Thank you very much. So first of all, an apology. Last time I messed up this criterion. I'll blame it on tiredness. This is what it should say. The criterion I wrote down was correct, and the proof was correct, but it wasn't strong enough for the examples, as many of you noticed. What I should have written was this, and the proof is essentially identical. So it's an exercise. Good. So the second lecture, I want to go back to Euler for a bit. So in the last lecture, we saw that Euler knew that the number zeta n so n bigger than 2 are very different for n even or n odd. So we saw that for n even, they're all proportional to powers of pi, even powers of pi. But for n odd, we expect that every odd zeta value is a completely independent number from the others. So Euler, after he proved his, a few years after proving solving the Basel problem, I suspect he wanted to see if he could find relations between the zetas to try to capture maybe zeta 3 or zeta 5. So he was looking for some, he said maybe zeta 3 is not pi cubed, but maybe there's some identity. So what he did is he had the idea of multiplying together two zeta values. And this appears in a paper several years after the Basel problem was solved. So he writes this as sum 1 over k to the m to the n. So this is a double sum. And he notices that this sum can be written in can be broken into different pieces. So the sum, you can think of it as a sum of a lattice. And Euler's idea is to split it into three regions. So the region where k is less than L, the region where L is less than k, and the region where k equals L. And so this last sum here is the same thing as the sum k is into infinity, 1 over k to the m plus n. So that's just zeta of m plus n. Sorry? Oh, thank you. But these quantities are new. So he discovers some new sums, and that's what his paper's about. And so the modern definition I'll say very little about this, but it's a huge subject of research. So multiple zeta value, you give yourself r integers, and r is greater than or equal to 2. And you define zeta of n1 and r equals sum 1 and this sum is finite, so it converges. I should say it's finite, it's a finite sum. So it defines a real number. So these were really introduced by Euler, certainly in the case R is 2, and his identity is the identity zeta m we put this down here. Euler shows that zeta of m times zeta of n is zeta of m comma n plus zeta of n comma m plus zeta of m plus n, whenever m, n greater than or equal to 2. So he was trying to generate as many identities as possible so that he could maybe find a polynomial equation for zeta 3. But we don't expect that to be true either. Oh yeah, so one quantity I should call here is the weight. The weight of such a notation is defined to be n1 up nr. This formula of Euler's generalizes. So if you want an exercise, you can try and compute. So exercise, find a formula for zeta m, zeta n1, n2 equals dot dot. And this generalizes. In fact, you can multiply any multiple zetas together and get a linear combination of multiple zetas. So any product of what are called MZVs, multiple zeta values, can be written as a linear combination in other words, the Q vector space spanned by multiple zeta values is an algebra. Or has a commutative ring structure. Yes. So, and we expect that all relations, like here you see the total weight, and the weight here is n, so this should be thought of as m plus n. The weight is constant everywhere. So we expect that the only relations that all algebraic relations respect the weight. So there are no relations between multiple zeta values of different weights. So I don't want to say too much about this, but already Euler proved lots and lots of other relations between these numbers. There's a vast amount of relations. They're not all yet understood. So there's a vast number of relations. It's an active area of research. But Euler, for example, showed that zeta 1 comma 2 equals zeta 3. And this is not obvious. Okay. So then this subject was then forgotten for about 250 years. So there's a paper in, I think, the 1750s, and it was completely forgotten for well over 2 centuries. So now I'm going to change topic a little bit, and before I move to physics, I want to introduce periods. So this is quite a classical subject, but it was popularized in a paper by Kontsevich and Zagier. And it's a fantastic paper, so I recommend looking at this paper. It's full of really interesting examples. And it's a good introduction to lots of different types of mathematics. So they defined, there's a naive and there's a sophisticated definition of a period. I'm going to give the naive one. So a period is a complex number whose real and imaginary parts are given by convergent integrals of the form I it's really an integral of a rational function over some domain. I'll tell you what in a second. Where sigma is a region defined by polynomial inequalities. So f 1 xn bigger than or equal to 0 dot 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 f, let's say n xn bigger than or equal to 0. Where P, Q, all the data are polynomials with rational coefficients. So it's essentially an integral in which all the data is algebraic. Everything is given by polynomials, and polynomials with rational coefficients. And you can, the definition is quite flexible. You can drop this condition of being rational, and there are generalizations, but essentially you always get the same class of numbers if your definition is reasonable. So let's do a couple of examples. So it turns out that most of the, or many of the most interesting numbers in mathematics are periods. So pi can be written as the area of the unit circle. Sorry. Well, let me write it this way. X squared plus y squared is less than or equal to 1. Clearly that's of this form. It's 1 minus x squared minus y squared is positive. So that's a period. This is the integral of 1. That's a rational function. Then we have the square root of 2 is the integral of dx from x squared is less than or equal to 2 and x is bigger than 0. So this is a region defined by polynomial inequalities. Everything is algebraic. Then the values of the Riemann zeta function many different ways to write it, but here's one. So this you can translate into this sort of thing. dt1 and n is bigger than or equal to 2. And to prove this, again, it's an exercise to prove this, but the idea is that you write, you do a geometric series expansion here. So dt1 over 1 minus t1 is sum t1 to the k dt1. Ooh. And let me just do the first integration. So if we do the first integration, we want to integrate t1 from 0 to t2. dt1 over 1 minus t1. And that will be, by this formula, sum t1 to the k dt1. And this is the sum k bigger than or equal to 0, 1 over k plus 1, t2 k plus 1. So I've done the first integration, but then you do the same thing. You plug this into here, and then do the next integration in t2, so that when you divide by t2, you lose a power here. When you do the next integration, that produces another k plus 1. And you keep integrating, and it produces in the end, I leave it as an exercise, you get the sum of k plus 1 to the power n, and that's zeta n. Okay, so that's a good exercise to spend some time thinking about. So the values of the Riemann zeta function at positive integers are periods. And multiple zeta values are as well. So zeta and r is minus 1 to the r let me do it this way. So here n is the weight. It's the number of integrations. And epsilon is 1, 0, 0, 1, 0, 1, 0. So here we want n1, n2, and nr. Can you check my sign? Yeah, that's correct. Okay, so those are some examples of periods, but there are many, many other interesting ones like elliptic integrals, and we'll see many coming from physics as well. So the first observation is that periods form a vector space. But it's actually a ring. Is a ring. That's an algebra. So the product of two periods can be written as a linear combination of periods. The other observation is that algebraic numbers are periods. So here we see that the square root of 2 is a period. It can be written as an integral. But in fact, all algebraic numbers can be written as periods. So we have the rational numbers contained in Q, contained in Q bar, contained in P, contained in C. And somehow the message of this concept in this paper of Kontsevich and Zagi is that this ring P is extremely important, and a huge amount of modern day mathematics occurs inside this ring P. We're not really interested in all complex numbers somehow. That the ring of periods is a more interesting subspace to think about. So many fundamental constants, I said this already, but many fundamental constants in maths, and as I'll explain in physics, are periods. And we saw by this argument that so E is, well, we don't know, but conjecture E is not in P. And Euler-Mascheroni constant is not in P. It's extremely difficult conjectures. So we know, of course, there must be many numbers which are not periods, but there is no explicit example of a non-period. So that's a very difficult problem. But we expect that E and gamma are of a different nature. And finally, somehow that Euler put his finger on the right concept in defining multiple zetas, that MZVs are contained in the ring of periods. And there's a way to see that multiple zeta values, in some sense, are the most, one of the simplest and most natural types of periods there exist in mathematics. They occur everywhere, many, many different subjects, and there are good reasons for that. But I don't want to talk about multiple zetas. I want to talk about what the... So if multiple zeta values are somehow the first most natural class of numbers we find in mathematics, Euler already discovered them, I want to ask the question, what are the most natural important constants in physics? Are they the same? And it turns out this is a very interesting story. So I'm going to switch now to some background in high-energy physics. And somehow what happened is as I said, multiple zeta values were abandoned for over 2 centuries. And they reappeared in both mathematics and physics at the same time in the 1990s. So now let me give you a very quick crash course in something called the theory of amplitudes. So a very brief introduction. To amplitudes. Okay, so subject called perturbative quantum field theory. Is the main mathematical framework for making predictions in particle physics experiments. So for example, for the Large Hadron Collider. So in this subject, we study particle collisions. Particle scattering. So what you have a collider, and you bring together some particles at very, very high energy. Say 2 particles, they come in at very, very high energy inside your beam, pipe, and something happens. They interact in some mysterious way, and what you observe, say 2, it could be 3, 4, 5, but let's say 2 other particles that come out the other side. And so for example, we observe 2 incoming and 2 outgoing particles. But it could be 3 or 4, it doesn't matter. And what you want to know, so this you cannot observe what happens here. This is a complete mystery. It's impossible to know what happens here. All you know is what goes in and what comes out. And you can measure the energy and the momentum of the particles going out very accurately. And you want to compare that with your theory. And if your theory doesn't give the same answer, that's because you've discovered a new particle has appeared somewhere here that you didn't think of. And that's how you discover, say, the Higgs boson. So what quantum field theory does is it provides a probability of observing something like this. More precisely, a complex probability, which is called a probability amplitude, so what you do is, quantum mechanics says that everything that could happen inside this mysterious bubble will happen with some probability. So we sum over all possible interactions. And each possible interaction is encoded by a Feynman diagram. Okay, so let's do some examples. So, for example, in the theory of quantum electrodynamics, which is the theory of light and matter, and by the way, this is the title of a book by Richard Feynman, which is brilliant. I recommend reading Feynman's book on QED. It's an excellent book. So here what we do is we have the diagrams are graphs built out of certain graph elements. So the graph elements here will be an edge with a directed edge depicting an electron going from left to right, or a positron going from right to left. It's the same. A photon, a wiggly line, and an interaction between photon and an electron. And what you do is you draw all possible graphs out of these pieces. And each graph encodes something that could happen. So here in this scattering process, the first particle may emit a photon that's absorbed by the second particle. And so this is how, say, electrons repel each other, because they send a photon from one to the other, and one electron gives momentum to the other one. That's how they can interact at a distance. But there are many other possibilities. This is a different one. Or here's a more complicated one. So the first electron goes along and it emits a first photon and then a second photon to the other electron. And you can get incredibly complicated diagrams. So let's do something a bit crazy. There's no limit. Let's put in another one, and we can have a virtual electron appearing. Oops. And we can have stuff like this. It gets very, very complicated, etc. And so the rule of the game is that you have to each of these graphs, you associate an integral. These are called the Feynman rules. To each G, to each G, associate an integral IG. So the IG can be thought of as some sort of probability of this, say, this particular event happening. And it's in general, it's a function. It depends on particle masses and their momenta and their energy and so forth. But we're going to look at a case where these integrals are just numbers. So this is a huge industry. There are, I don't know, maybe not thousands, but hundreds of people in the world who have been computing these integrals full-time for well over 50 years. There are computers running night and day calculating these integrals in order to provide predictions for particle theory experiments like the LHC. There's a very, very big community of people whose lives are devoted to doing this. So what we do is then, given our process here, so to electron scattering, we have, obviously we can't compute every single IG, it would take infinite amounts of time, but we compute as far as we can. And ideally we would sum over all graphs. But obviously we have to stop at some point and take the sum of these integrals, that's a complex number, and we take the norm squared. And that gives us a real number, which is essentially the probability of observing this in experiment. And the hope is that the graphs, as the graphs get more complicated, so in physics it's called loops. The loops is the number of independent closed circuits. We'll see that later. So you can order the graphs by how many loops they have. But graphs with higher numbers of loops represent finer quantum corrections to what you are observing. So it's hoped that it's like some kind of Taylor expansion. As you get further and further down, you get smaller and smaller corrections to the probability you want to compute. In practice, there are all sorts of very difficult mathematical problems behind this, which I won't talk about. So what we want to do is we'll consider a very simple part of this, a part of the standard model of physics, where there will be no masses and no momenta. There'll be no, these aren't functions, there'll be numbers. Of course, there are masses in momenta, but they're sort of hidden somehow. But what I will tell you is a genuine contribution to the standard model, where the IG are numbers. But since we get numbers, it's much close to pure mathematics. Okay. Right, so that was the introduction. So we're going to assign numbers to graphs. So to do that, we need what are called graph polynomials. So we're going to write down some graphs and write down some integrals associated to graphs. So in the theory we're going to look at, the graphs G will always be, of course, finite. They're always finite in this business. They will be connected. And they are usual graphs, so they have only one type of edge. So they're just graphs, connected graphs. And then to each edge, E. So EG denotes the set of edges. We assign a variable. Alpha E. So it's sometimes called the Schwinger parameter. So to every edge we have a variable. And then we define the graph polynomial denoted psi g is going to be a polynomial in the edges of the graph. And it was defined by Kirchhoff. Can never remember. He's got two H's and two F's, I think, in about the 1850s. So he was studying resistance in electrical circuits, and he invented this to do that. And it is defined by psi g equals sum So these are absolutely fascinating polynomials with lots of remarkable properties. So the definition is over spanning trees. So I should say a spanning tree T in G. So for me, subgraphs are given by sets of edges in a graph. You choose a subset of edges, and if an edge contains a vertex, that's a vertex of your subgraph. So a spanning tree is a subgraph which is connected, simply connected. So if you don't know what that means, it means that it has no loops in it, no closed circuits. So that's what it means to be a tree. And spanning means that it meets every vertex of G. In other words, the vertices of T equals the vertices of G. So V is vertices, set of vertices. Okay, so let's do an example. Thank you. I'm ready for time. Okay. So let's look at this graph. And I'm going to number the edges 1, 2, 3, 4. So let's look at the spanning trees. So we want subgraphs which meet every vertex but do not contain a loop. So we can have, and which are connected. So we can have this, 1, 2. We can have 1, 3. We can have 1, 4. 2, 3. 2, 4. And that's it. Okay, you can't have a triangle 1, 2, 3 because that is not simply connected. So those are the only ones. And then to get the graph polynomial, to each such spanning tree we get a monomial here. And it's the product of variables which are not in the spanning tree. So here the variables not in spanning tree are alpha 3, alpha 4. Perhaps I should just label these for clarity. 1, 4, 2, 3, 2, 4. So alpha 3 plus alpha 2, alpha 4 plus alpha 2, alpha 3, plus alpha 1, alpha 4, plus alpha 1, alpha 3. So a general fact, as you can see, is psi g is homogeneous. Of degree equal to hg, which equals the loop number of loops, or the number of independent cycles. Or if you prefer, if you're more sophisticated, it's just the first Betti number of G, the first homology group. And a good exercise is to do this graph if you just have sort of polygon, I don't know, 1, 2, oops, 2, 3, up to L, let's call this N, then psi G alpha 1, alpha 2, plus alpha N. Okay, so we've assigned to every graph we've got a polynomial. Now we want to write down an integral using this polynomial. So this is what's called the Feynman residue. For technical reasons, I don't want to go into. So we're going to assume the number of edges of our graph equals twice the number of loops for now. And let's number the edges of G by 1 up to N. So NG. NG equals. And so the Feynman residue is integral over a cube, hypercube, of d1 d alpha ng minus 1 over psi g squared, in which I set alpha ng equal to 1. So what you do is you pick one edge, in this case the edge with the largest number, and you just set it to 1, and then you just integrate 1 over psi squared, where all the alphas go from 0 to infinity. So the first remark is that it does not depend on this which edge we set to 1, on the choice of ordering or numbering. So there's a more sophisticated way to write this as a projective integral, and you can see it doesn't depend on this choice at all. But I chose to do this because it's more elementary. And it is finite. So it can be infinite, if and only if, for all subgraphs gamma strictly contained in G, the number of edges of the subgraph is strictly bigger than twice the loop number of the subgraph. So this is a theorem due to Weinberg. So let's do an example, and then I can illustrate this convergence condition. So this graph it does not have a convergent integral. So this contains a subgraph, it's called a divergent subgraph, which has two edges and one loop. So this integral is not finite. So this one's no good. It has what's called a subdivergence.
It also has two types of vertices.
Sorry?
It has two types of vertices. You said that we only have one type of vertices.
Oh, the degree can be anything. I said there's one type of edge. So there's one type of edge. There's no. I meant there's no no photon lines. That's what I meant. But the degrees can be anything. All these phones going off. I'm worried about.
You assumed that you have such a relation. No edges like is equal to.
Yeah, I assume this.
Okay. It's possible to define the integral. Then in this lemma, or in this claim,
Here.
it's finite.
Yeah, this theorem. Yeah. It's not obvious. But basically, what happens is, if you have a subgraph like this, then what happens is, if you let alpha 3 and alpha 4 go to 0 very fast, you can calculate the order of growth of this, and it forces the integral to diverge. It's a bit more subtle than that, but it's in physics it's called power counting. The presence of such a subgraph will, you can see, cause this to blow up in the region where the edges get very small. And the content of the theorem is saying that the converse is true. That if no such subgraph exists, then it must be finite. So it's a theorem, it's not completely trivial. So let's do the first example. So the simplest example is G is this. It's the only example we can really do on the board. IG is going to be integral from 0 to infinity d alpha 1. Oh, sorry, I forgot to say here psi g is alpha 1 plus alpha 2. So this is going to be alpha 1 plus 1 squared. And this is 1. Okay. So this Feynman residue is 1. But in general, so maybe I can use this as minus 1 over. In general, they're very hard to compute. Not that one. I mean, this one is not hard, but the other ones, the general graphs, are very hard to compute. So here's some examples. So these are examples of graphs where they do not contain a subdivergence, so that the integrals are finite. So let's draw them here. So we have the wheel with 3 spokes. So here's the graph. And the integral is 6 times Riemann zeta of 3. So we see the Riemann zeta function occurring as the integral associated to this graph. This is very difficult to compute. The psi g has 16 terms. Next example, wheel with 4 spokes. Zeta of 5. Something called W3 double dot, which is this graph, which I think was on the poster. This gives 36 zeta of 3 squared. So these are very difficult to do, and they were done systematically by Broadhurst and Kreimer in the 1990s. And the most difficult graph, or one of the most difficult ones that they managed to compute, is this complete bipartite graph, K through 4. And this gives 27 over 5, zeta 5, comma 3. So completely amazingly, after having disappeared for 250 years, the multiple zeta, zeta 5, comma 3, reappeared in physics. And at the time, nobody knew what this number was. So the physicists who computed this, Broadhurst and Kreimer, they went around to mathematicians saying, we've got this double sum, can anyone tell us what it is? And it took some time to realize that Euler had invented them 250 years earlier. And it's a conjecture that zeta 5, comma 3 is algebraically independent from the single values of the zeta function. So it cannot be written as a polynomial in single zetas. And this was important because it changed completely the face of the subject, because people expected quantum field theory to be simple and easy to understand, nice polynomials in zeta values. And this new number appeared, which changed expectations completely. So that was an amazing discovery. I think I have 10 more minutes. Do I? Okay, good.
So there is some classification of such.
Which ones?
They have some names.
No, they just happen to be small. All small graphs have names, just because they've been studied. I mean, I'll tell you what's known. There's been a lot of work on this. So it's known that the all the wheel graphs are zeta values. They will give single zetas. We also know there's something called zigzag graphs, like this. Zn. This is something that I did with Oliver Schnetz. Is some rational number zeta 2n minus 3. I could also prove that infinitely many IGs are multiple zeta values. And it was conjectured for a long time that all these integrals should always be multiple zeta values. There are many, many, many examples of multiple zetas, and you can prove there's an infinite class which are multiple zetas, but not all multiple zetas occur. So you never find any zeta of 2. There's never any zeta 3 times zeta of 2, etc. So it's a very strange family of numbers, and we don't fully understand what they are. So to cut a very long story short, when I was a student, there was a big conjecture that these were all multiple zetas, and I tried to prove it for a while, and I could only prove this, but it turns out now we believe it's false. So we have examples of graphs which are very large, which we can prove should not be multiple zeta values. They're related to completely different mathematics. This took a long time to do, but I'm not going to talk about that. But the conclusion is that somehow the numbers coming out of physics are similar, but not the same as the most natural class of numbers we like to study in mathematics.
Just we don't know theorem.
Sorry, what's the?
Is it theorem that it's impossible to obtain this?
Well, the problem here is that you have it's like an irrationality conjecture. You don't, to show that zeta 2 doesn't occur, you'd need to know that zeta 2 and zeta 5 are not proportional. And we cannot, as I explained last time, these incredibly difficult conjectures, we don't even know if zeta 5 is rational. But if you assume some transcendence, some standard transcendence results, then we can prove these all rigorously. And we can prove, you can write down an example of a graph that I constructed with Oliver Schnetz that is not a multiple zeta value, that's algebraically independent. But that took many years to do. So if we assume some transcendence results, because that's extremely difficult to prove statements about actual numbers, but if we assume something, then we can say a lot. But there is no natural mathematical definition of this class of numbers. We know they're periods, but which periods is a mystery. So I wanted to, before finishing, just quickly give some properties.
How much time you will have here?
3 minutes.
Ah, okay, so you will finish, okay.
Yeah, I will finish.
Yeah.
Is there so I want to just, before finishing with this, show that there's a lot of structure here. These integrals have lots of interesting properties. So one, let me say, if G is planar, then it has a planar dual. And if it's convergent, then IG has the same residue as its dual. So the dual of a graph, for example, if you have a graph like this, then you put a vertex in every face, including the face at infinity, and for every edge you connect them corresponding vertices by an edge. So it says that, so that's the example of a planar dual. So that's one identity. There are many more. Perhaps I'll give one more that explains this structure. So if, so how did I explain this? Okay, so if you have two graphs of this form, so if you have G1, a graph with two vertices connected by an edge, which are 3-valent, and G2 E, let's call this G and G prime. So if you have this sort of structure, so you have an edge connecting two vertices of degree 3 and our stuff, and this graph is called G and this graph is called G prime, then you can form the two vertex join, which is where you identify these two vertices. You identify these two vertices, and V2 equals V2 prime. You delete edge E and E prime, and you keep all the rest. And delete E, E prime. Then the theorem is that G, the two vertex join, is the product. So there's an interesting multiplicative structure here. And so if we do this example here, example, if you put G is the wheel with 3 spokes, then if we join them together, so if I try to draw this, draw it like this, and I two vertex join this to this graph, then I get this graph, which is exactly this one here. And so this result is exactly the square, yeah. So this can be proved by changing variables alpha e goes to alpha e inverse. That's the proof. This you can prove as an exercise. It's not so difficult, but there's a proof written in one of my papers. And there's one more property that's quite subtle that I wanted to give, but should I risk the anger of the economists?
We can take at most 5 more.
5 minutes. Okay, this is just 2 minutes.
ICMU, because there is some problem with one and another. We will have TR steps, but
Shall I do it, or I don't want to encourage? Okay. So then the final. So there are many, many identities, and we do not know them. So it's like multiple zetas, that they have a multiplicative structure and lots of relations, which are not fully understood. And then perhaps the most interesting one is called completion. And the proof of this would be really hard unless you knew a lot of physics. I mean, it would be almost impossible to find this unless you knew some physics background. So we assume that, suppose all vertices of G have degree at most 4, which is a physical. I mean, graphs in physics tend to have this property. So it's called 5-4 theory in physics. And if G has more than 2 edges, then you can show G must have exactly 4 trivalent vertices. So it looks like this. That's drawn in blue. So for example, for the wheel with 4 spokes, it has exactly these 4 trivalent vertices, and it has one 4-valent vertex in the middle. And what you do is you create a new vertex, and you connect it to the 4 trivalent vertices. So G hat is the 4 regular graph where we connect a new vertex to the trivalent ones. So we get a graph here, G hat. And the theorem is that if G1 hat is isomorphic to G2 hat, then IG1 equals IG2. And this is really subtle, because so what it says, you can take a graph, you can add a new vertex at infinity and complete it in this way. And to get back the old graph, you just delete this vertex. You get back the with 4 spokes. But you can delete any other vertex, and typically you get a completely different graph. But the theorem says that the residues are the same. And if you look at what happens on the graph polynomial, they are completely unrelated to each other. So there is an integral transformation that goes from here to here, but it's very subtle and passes through something called momentum space in physics. So this is really non-trivial. And there's many, many other proper identities we know, and the list is far from complete. So I think I should really stop there.